Last year, I made a video all about how we don't know how long a day is on Saturn, i.e. we don't know how long it takes Saturn to fully rotate on its axis. But now we think we do. So as a quick summary of this problem, it is notoriously difficult to measure the rotation rate of the gas giants because unlike for the rocky planets, there's no fixed objects on the surface that you can pick to time how long it takes to come back round to the same spot because everything is just, swirling around in the thick gas atmosphere in the same way that sort of clouds move around in Earth's atmosphere. Instead, what we do is we use the radio emission that's given off by electrons trapped in the magnetic field of the planet. And that radio emission, as the planet rotates, essentially beams like a lighthouse. And this is the same process that produced a lot of the aurora on planets as well. The problem for Saturn is that the measurement that Voyager took back in 1980 and the measurement from Cassini in 2005 differed by 6 whole minutes. And in my previous video, I talked about how unlikely it was that the real actual rotation rate of the inside of Saturn had actually changed by 6 minutes because it's difficult to slow a planet's rotation down like that. You would need an incredibly large force to slow it down that much in that short space of a time. Instead, it was probably something to do with the measurement. And in my previous video, I said there's 3 things that could explain this. Either the Voyager and Cassini measurements were wrong in some way, but they've been looked at many, many times and people can't find anything wrong with it. Or it really did change by 6 minutes, which we just heard wasn't likely. Or 3, that there's some new science here that we don't yet understand. Now, there's lots of different ideas, hypotheses been floating around for decades since that Cassini mission with the 6-minute difference first came in. And one of the ones that I talked about in my previous video was this idea that Saturn's moon Enceladus, which has these huge geysers of water that are fired off from sort of Grand Canyon style trenches in its surface, which then put more charged particles into sort of this ring around Saturn, which could then cause a drag force on what we call the magnetosphere, this magnetic field region around Saturn, which could then at least change the measurements that we get using the radio emissions by 6 minutes, even if the interior motion of Saturn hadn't actually slowed down by 6 minutes. Now, at the time I made that video, the Enceladus hypothesis was very popular. We had observations, we could actually test it, but it wasn't quite right. There was still a few things that it couldn't quite explain. So there is another option we can look at, one that people didn't think it would be possible to measure or to test until now. The idea is that the radio emissions that we use to track this rotation of the magnetic field of Saturn are actually affected not just by the movement of particles in the magnetosphere, this region around Saturn with the magnetic field, but also the movement of particles in Saturn's atmosphere itself, like winds in Saturn's atmosphere. Now, to spot this, you actually have to observe particles in the upper atmosphere of Saturn itself, something Cassini couldn't do, but that Chowdhury and Stallard and collaborators have managed with the Keck telescopes on Mauna Kea using its infrared sensitive spectrograph that splits the light coming in into all of its component wavelengths so you can see the big peaks where specific molecules or atoms are present. And so what Chowdhury and collaborators looked for was emission from a molecule called trihydrogen cation, i.e. 3 atoms of hydrogen sharing 2 electrons, so there's an overall positive charge. We call it H3+. The emission from this molecule gets Doppler shifted and broadened out because all the H3+ ions are moving in Saturn's atmosphere. And so with this data, you can actually make a map of the direction and speed of the winds in Saturn's atmosphere, which they did using this Keck telescope for over a month, and found there's a twin polar vortex on Saturn. So above my beloved polar hexagon storm that's raging deep down in Saturn's atmosphere, that was one of the first videos I ever made on this channel was explaining that. Above that, you've essentially got particles that are moving in a figure of 8 shape to give these 2 vortices moving in opposite directions right at Saturn's pole. The idea is that this movement of particles then affects the movement of charged particles in the magnetosphere around Saturn, which give rise to Saturn's aurora and then the radio signals we use to measure Saturn's rotation rate. So because this twin vortex is, ever changing and messy, right, the radio emissions are as well, and so they're incredibly variable, not tracing that true rotation rate of Saturn and giving this big 6-minute difference between Cassini and Voyager. It's a really incredible result, and one that's really neat too, because it explains so many different things. So I had a chat with my colleagues who were the lead authors on this study, PhD student Nahid Chowdhury, who led the analysis, and his supervisor, Tom Stallard, both from the University of Leicester here in the UK. I started out just by asking them to summarise, what's new that we've learned from this study in their own words.
So we have learned that there's a different way that the aurora at Saturn are generated, and that is fundamental. And we've also finally addressed one of the longest standing mysteries regarding the rotation rate, the length of a day on the planet of Saturn. So yeah, there's two major outputs basically from this.
And that must feel incredible.
It does, yes. And I still remember last year, it was probably in April or May, when I had a meeting with Tom, and I was showing Tom the plots that I had. And at the time he said, well, it looked as though that we'd actually managed to answer the question that had been that had bugged people for ages. And then Tom said to me, you know what this means? This means that there's only two people in the world that know the answer to this question. And it's us two. And that just felt so profound. It was amazing.
How long have you been waiting to know that as well? Because obviously other people don't know, but they don't know that they should care to know almost. But how long have you been working on this problem, Tom?
I was around when Cassini was on its way to Saturn. It hadn't arrived yet. I remember the excitement of the arrival at Saturn. There were already murmurs of a problem because people were looking at data from other measurements before Cassini arrived that seemed to show something was up at Saturn, that the rotational period as measured in the way that we've measured it for everything else in the universe that doesn't have a solid surface. Well, if it's a solid surface, it's really easy. You just look at the mountains drift by and you know what the rotation rate is. But if you don't have that, if you've had clouds that distort that number, then you just look at the magnetic field. It tells you what the interior is doing. And some of the observations that they were doing measurements back in 2000, 2001 were off, and they were trying to understand why they might be off. And then as soon as Cassini arrived, I mean, it's literally the first press release NASA put out, basically, before they even did any other measurements, because one of the easiest measurements you can make when you arrive at a planet is just look at the radio signal. And you do it on the way in just to test that the radio signal is working, right? And it came up with a number that was minutes off in terms of the rotation period of the planet. How quickly is that planet spinning? Well, it's spinning 6 minutes faster than it was 10 years ago, which is insane. I mean, that's impossible. So that was the big news that everyone was talking about when the mission started. So it's been a long journey. About 10, 12 years ago, a colleague of mine who did his PhD and immediately left science to do physics. He teaches A-level students. Nice. It's what he always wanted to do. That's why he did his PhD, but he's also one of the best scientists I've ever met. That's Chris Smith. He wrote this profound paper back in 2011 where he went, actually, it's the atmosphere of Saturn. This atmosphere of Saturn is one way that you can make this process work. Literally the only thing you can do to test this theory is look at the ionosphere and see where it's going. You measure what it's doing, how it's moving, and that tells you the answer. It's as simple as that. It's a really simple premise. There's two options. The magnetosphere is driving it, or the atmosphere is driving it. Option A, the magnetosphere, is how all aurora in the whole universe has ever worked. And option B is a completely new kind of aurora that no one has ever seen or understood, but happens to run in exactly the opposite direction. So all we had to do was look and see. It sounds really simple, but it's really not simple.
No.
You apply to the biggest telescope in the world and hope for the best. So that's what we did. We're very lucky that the Keck telescope, which is no longer the largest telescope in the world, but is probably still the most highly regarded telescope on Earth in terms of the breadth of the science that it can produce. Only through a whole month. So we the total observing time was quite short, but the time span that we were observing for was a month.
Yeah.
And it gave us this amazing data set.
Amazing. So Nahid, I'm really curious to know what it was like to then join the team as a student.
At first, I was quite apprehensive because it was a large data set. It was much larger than the one that I'd been working on up till now. And yeah, the way it was structured, it would have meant that I need to chip away at it slowly, bit by bit. And it took a very, very long time. I mean, I started looking at this data in 2019. And it might have even been at the later end of 2018. So yeah, it's the best part of 2 or 3 years to get to this point. But yeah, the data were unique in the sense that they had been scans of Saturn's aurora. In the past. What we've had normally is access to just data from a single position on the planet. But these data allowed us to produce maps of these auroral emissions. And so, yeah, in that sense, it was a lot more involved to be able to go from the raw data into a result, which is why it took so long.
Because I remember my time as a student where I think at first I didn't always quite understand why I was doing something. I knew what I had to do. And so I just sort of plowed on with it. But it wasn't until the very end that I was like, oh, wow, that's why. Did you have a similar sort of experience working with this, that it was only at the end that you realized the magnitude of quite what you'd done?
Yeah, without question. At the start, I just thought, yeah, this is going to be a bog standard analysis. We're doing it slightly different. Yes, we're going to be grouping the data into the magnetic phase of the planet, but I wasn't really expecting that to reveal anything, if I'm honest. But then, yeah, Tom's guidance really and determination to make sure that the data did actually produce something was what really helped to drive the result, and indeed careful analysis.
And early on in our analysis, where we were getting data through, it was apparent we'd seen something. We could see a clear blue shift in the pole, and that's what I thought the best possible result would be. And we were looking at the data. There was a moment where we were looking at two separate sets of data, one looking effectively 90 degrees off of the other as the planet rotates. And I realized that in the weird way we had processed the data, we could do something we never normally are able to and put them together. You take one, you add the other in, and you just make a two-dimensional vector map of the flows. So I told Nahid to do it. He said, okay, I'll do it. And I said, no, do it now. Do it now.
Right this second.
When you put them together, instead of a single data value, we could see the flow. We could see the actual twin cell vortex that powers everything.
Yeah. It
wasn't just a simple, we think we've seen something. It was writ large. It was absolutely obvious. It was like a thunder strike with a deafening boom of a result, And so we both just sort of sat there looking at the screen for a while. Because, in that moment, that you have answered the question that people have been asking you to answer for decades.
Nahid, do you remember it the same way? I'm intrigued to know.
I do. Yeah, Tom just said, look, I found this piece of code which is able to produce a vector map. It might be interesting to apply it to your data. And I just thought, yeah, sure, I'll leave it to me. I'll look at it in a week or so. I had other little bits and pieces going on at the time. And then Tom was like, actually, no, let's try and do it together. And so I was sort of forced to do it on the spot. But yeah, as he says, when that map came out, you just thought, what is this actually possible? Is it really plausible that we're able to produce a view like this from the data that we have? And that's the point where the penny really dropped for me, and I realized, you know what, this is an enormous result.
I mean, I feel like with every scientific paper, you always have more answers, more questions still than you have answers. So what is next?
For me, I think the best thing to do in a few years' time is to observe the southern aurora in the same way that we did the north, and see if we can see, if not an identical vortex system, or at least something very similar. That would be immense. But we're going to have to wait until at least 2025 for that to become a possibility.
Why is that?
At the minute, the way Saturn appears from the Earth, we are seeing the rings sort of facing us. They're tilted towards us. And so we're seeing the northern aurora mainly. But over the course of time, that will eventually change. The rings will become side-on, and then they'll be tilted away from us, which will show us the southern aurora. And yeah, there was a study which one of our colleagues, James O'Donoghue, did, where he used data that was taken of both the northern and the southern aurora at the same time from Keck. That allowed a direct comparison of temperatures in the north and the south. And
So what do you actually expect to happen? Do you expect there to be another of these like twin vortexes, or do you expect there to be nothing? Like if there was nothing, would that sort of throw everything out, or would it just be really difficult to explain? Or
if there was nothing, I think that would be an even bigger result than if there was a twin vortex there. We are expecting, I think, sort of the opposite of what we're seeing. So twin vortex, but the flows might be in the opposite direction, I believe. Nice. Based on the modeling that we've seen. So yeah, fingers crossed, if someone were to take that data and analyze it in the way that we've done, if they see the twin vortex flows again, but for the south, that would be immense. If they don't see it, then that is, probably even bigger as a result.
Nice. Well, I have one last question for you both that I feel like my subscribers would think I was remiss if I didn't ask you, because it's the topic on everybody's minds at the minute. And that is, could you use the James Webb Space Telescope to help with these investigations of Saturn?
We desperately want to use James Webb to do this. We have observations of Jupiter and Uranus and Neptune, looking at the kind of iron that we look at in the guaranteed time and in the early release science. Saturn is the one thing that we don't have data for in the current plan.
Too close to the sun?
It's just, there's so much demand for that time.
I would have been like Saturn's top of the list, but that's
you would
just
hope.
Me.
We've put proposals in, we'll continue to do that. There's two things we want to look at. One is, can we see hotspots that are causing this flow, and that they might be able to resolve those out using the incredible sensitivity. And the other thing is the work that James O'Donoghue is doing, looking down on the equatorial regions and the ring rain and all of that kind of stuff. It's the perfect thing to get something that has 100 times more sensitivity than Keck to look at. But there are 100,000 other amazing things to look at in the universe that are equally important. So we'll continue to plug away, and hopefully we'll get time to really start answering those questions. But James Webb is such a profound change to infrared astronomy, and it's infrared astronomy is the lifeblood of everything that I do. So we're so excited as excited as everyone else, because as much as there is like a part of me that's interested in the science that I want, I'm as geeky about this for every other field of science that I'm not involved with.
Yeah, me too.
The profound things that we'll find out there, it's going to be amazing.
It is. There's only one last thing for me to say, and that is a huge congratulations to Nahid, because an hour and a half before we went on this Zoom, you submitted your PhD thesis. That is incredible, and I hope all of my subscribers wish you many congratulations in the comments below, because thank you incredible achievement. Incredible.
Thank you so much to Tom and to Nahid for taking the time to chat to me about their work, and especially to Nahid as well. Just submitted his PhD thesis. I was taking valuable celebration time away from him on a Friday there. But it really was just this fascinating insight into the world of, solar system astrophysics, which is just so removed from what I do in terms of like studying galaxies and black holes, especially because it was all about my favorite planet, Saturn, as well, which I could talk about for hours. But I think what was so revealing during that entire chat I had with them, and the longer chat as well will be on my channel in a couple of weeks' time as well, it's just that there's so much that we still don't know about our own backyard of the solar system, and especially about Saturn. Before we get to the bloopers, I just want to say a huge thank you to Brilliant for sponsoring this week's video. Brilliant is an interactive STEM learning platform that helps you to fully get to grips with concepts in science or maths or computer science by guiding you through these engaging, hands-on courses that get you to learn by doing. Plus, if you get stuck, Brilliant provides these more in-depth explanations to break down a topic even more so that you can learn at your own pace. I know a lot of you love last week's video talking all about the diffraction patterns that you get through the James Webb Space Telescope's optics setup, and so you might want to know more about how light and how waves behave after watching that. Well, Brilliant has a course on just that, waves and light, so you can better understand how waves behave when they meet obstacles and each other, like in this lesson on interference of light to give constructive and deconstructive interference, something that's used in noise-cancelling headphones to get rid of unwanted sounds as well. So if that sounds like fun to you, to get started for free, head to brilliant.org/Dr. Becky, or you can click on the link in the video description down below, and the first 200 of you will get 20% off an annual premium subscription. So thank you so much to Brilliant for sponsoring this video, and now roll those bloopers. But the Chowdhury and Stallard collaborators have managed with the Mauna Kea telescopes, with the Keck telescopes, or Mauna Kea, but the Chowdhury and Stallard collaborators have actually managed using the Keck telescopes, can't I get this? But the Chowdhury and Stallard collaborators have managed using the Keck telescopes on Mauna Kea with the infrared sensitive infrared sensitive spectrograph. Even slow, I can't even get it. You've got particles in the upper atmosphere swirling this like figure of 8 shape with these two vortices. Vortices sounds weird, but vortexes also sounds weird. Space is hard, words are harder. Now this is notoriously difficult to... Notorious.